it being able to describe the action potential. But I'm going to get rid of this axon up here. I'm going to get rid of my negative potential difference right here. Now, this is your answer. Well, more than that, I'm going to put something up there. So my potential difference is going to be on my vertical axis, my PD, potential difference, negative and zero and positive right there. Okay, now here we have kind of a flat line. The first instruments that looked at this, it was a flat line. You couldn't see any small waves in it at all. Nowadays, with better equipment, these things have a wave. This is a resting potential. This is resting. I want you to label this as resting, R-E-S-T-I-N-G. Okay? Oh, this is over a period of time right here. I'll make it a capital T. Over a period of time right here, this is resting, R-E-S-T-I-N-G. Now, it is negative, again, because of the anions that are trapped inside the cell. Now let's stimulate that sucker. Let's stimulate that sucker. Let's activate that nerve, activate that neuron right there, and see what happens. Well, what we find out, the sucker jumps all the way up here to positive, comes right back down to negative, overshoots it, and goes right back to resting. And he sees this over and over and over again in this frog, this poor old frog from South America. Wish I had enough money to invest in it in. But hell, back in the 50s, I wouldn't think about frogs. It's a beating frog legs. Really a different story here. Now, we're almost done with this right here. Vertical line, horizontal line, potential difference, negative, zero, positive, T for time right here. Resting, sodium in, Na in, potassium out. Sodium comes in to change the potential difference to positive. Potassium goes back out to change it back down to resting. I overshoot it right here. I overshoot it right here. Okay? Draw me an overshoot. It's very important about the overshooter here. I overshoot it right here before I get back to resting. That's all I want. You put down overshoot. We can call it hyperpolarization. You can get that. Hyperpolarization is when I overshoot back to resting. Hyperpolarization. H-Y-P-E-R-P-O-L-A-R-I-Z-A-T-I-O-N. H-Y-P-E-R-P-O-L-A-R-I-Z-I-O-N. Hyperpolarization. P-O-L-A-R, yeah. Somewhere there's hyperpolarization. It's this area right in here. I overshoot my resting when the potassium ions come back out. Well, this is drawing and labeling the signal that the neuron generates. Name it, action potential. Draw it, tell me about potential difference. Draw me a cell, positive ions, both. Put one positive ion on the inside, one positive ion on the outside. Put me a negative ion on the inside right here, and label that a negative resting membrane potential. Negative potential difference. So I want you to define potential difference for me, the difference in charges inside the cell versus outside the cell. That's going to be part of this answer. It's a heck of a question, but this is what it is right here. Now, give 3 examples of targets of what a neuron might regulate, okay? Now, I'm going to erase this right here, go back to my neuron again. Since this is a lecture on neurons, we're going to draw that blame neuron again. Don't have to label it, but I got to go back to it again. Then we'll look at the type of regulation that we have, and we'll look at the area of the regulation. Okay. Now, not all of them look like this. This is a typical one. This is probably in the minority, but I like to draw this right here. The rest of them look kind of funky. They really do. So if you want to see some pictures of neurons, go on YouTube or go on Wikipedia. Look up neurons. You're going to find a lot of different neurons, all right? Some of them don't have an axon at all, axonic. But I don't care about those. I like to explain this one right here. Okay, now, my signal, my action potential is going to go in this direction right here. My AP goes in this direction right here. Still don't need this in your answer, not yet right here. Well, what does this neuron regulate? Now, we are wired where we have very specific regulation by very specific neurons. But that I mean, one neuron will regulate only one type of target. For instance, a skeletal muscle, okay? So I'm going to write down possible target as a skeletal muscle, S-K-E-L-E-T-A-L. A skeletal muscle, okay? Now, that might be the target right there. The neuron might regulate another neuron. Have a lot of communications inside the brain, so neuron to neuron transmissions occurs. But it's not going to be a neuron to a skeletal muscle and to a different type of target. It doesn't work that way out here. Skeletal muscle might be one target, or a neuron, or it might be a cardiac muscle. Since we know something about the heartbeat, since we know something about the SA node right there, those are specialized muscle cells right there, but they act like axons right there. What regulates the SA node, remember the pacemaker right there? That's a neuron, all right? So we might have, instead of skeletal muscle, we might put down cardiac muscle as an example of another type of target. We'll write down cardiac muscle up here. Now the regulation is simple. Either turns it on or turns it off. Either stimulates it or it doesn't stimulate it. If it doesn't stimulate it, it inhibits. So I want you to write down stimulate or inhibit. Stimulate, positive, stimulate. I'd rather have something other than a plus or minus. I'll take a plus and minus, but I'd rather have you write down stimulate or inhibit. The type of regulation, stimulate or inhibit. Stimulate or inhibit. And believe it or not, when it inhibits, it just doesn't stimulate it. How you like that? When it doesn't stimulate it, it inhibits it. I like it. But anyway, stimulate or inhibit. Now, give 3 examples right here. Now, the last thing for right now, I want to take a look at the area of the communications between this right here, between the end of the teledendria, that's the end on the right-hand side right there, and a skeletal muscle, all right? We know more about this regulation than any other one, so I got to turn this same, I'm going to rotate it 90 degrees, and I'm going to draw the end of the teledendria, and I'm going to draw my target, my skeletal muscle cell. Hang in there with me. All right. Doesn't look like anything like what I drew up a minute ago, does it? Now, this large swelling here is the end of the teledendria. So I magnified this. I magnified the hell out of this right here. This is the end of the teledendria right here. End of the teledendria. All right. T-E-L-O-D-E-N-D-R-I-A. This is the end of the teledendria right here. Okay. This is my skeletal muscle. Skeletal muscle cell. Okay, now, my objective reads right here. Draw and label a synapse. This is the synapse. It's got 3 components right here, all right? This is the synapse. I'm going to label parts 1, 2, and 3. Parts 1, parts 2, part 3. 1, 2, and 3. Well, I'm going to label part 2 first because it's going to make part 1 and part 3 a reference to part 2 right there. Part 2 is the gap in the synapse, called the little drum roll, synaptic gap. Part 2 is the synaptic gap. Part 1, part 2, part 3, S-Y-N-A-P-T-I-C gap, G-A-P. Synaptic gap. Now there's a membrane in front of that called the presynaptic membrane. The membrane in front of the synapse is the presynaptic membrane. P-R-E S-Y-N-A-P-T-I-C, membrane. Alrighty, sorry about that. M-E-M-B-R-A-N-E, presynaptic membrane. I bet you can guess what the one below it is, though. Pre versus post. Number 3 right here is a postsynaptic membrane. The postsynaptic membrane, P-O-S-T-S-Y-N-A-P-T-I-C, membrane. Postsynaptic membrane. Well, that's the synapse. That's where the communications come from between a neuron and its target. Irregardless if it's a cardiac cell, if it's another neuron, if it's a skeletal muscle cell, if it's a cell itself. Okay, this is the communication area, the synapse itself. Okay, I'm going to stop right there. I'll pick it back up with That was number 5. That was number 5 up there. I did not put number 5 up there. I'll pick back up with number 6 here shortly. All right?